All right, so our notes, chapter 1.5 and 1.6, we're going to continue our work with analyzing quantitative data and looking at another type of graph. And that's what the note starts off with, is another type of graph that you can display quantitative data with, and that's histograms. Histograms are great when you have a large amount of data. Okay? So when you have large amounts of data, histograms are a great way to summarize it. Because instead of having like a dot or like a number representing each and every point, what happens is you're going to basically have these bins or intervals in which you're going to collect the data within. A histogram looks very much like a bar graph, but remember, bar graphs are specific to categorical data. Since we're going to be dealing with quantitative data, okay, when doing a histogram, your bars, okay, will be connected together and they'll represent intervals. So it might go 10, 20, 30, 40, and maybe I'll go like this, 50. Okay? And so what happens is each of these bins represent scores within an interval. So these might represent something like scores between 10 and 19. And the reason why I put 19 there is because you might be saying, well, 10 to 20. 20 is not included in this bin. So this one would be between 20 and 30, but not including 30. 30 and 40 and not including 40. That's one of the key pieces to note about histograms. Okay? Now, when you make your bins, you want to make them all the same width. Okay? Because if you don't, it's going to give you a disproportionate picture of what the data looks like. Okay? So when you do a histogram, we have kind of three steps here that you'll do. You'll want to draw and label your horizontal scale, mark the possible values that you have on it. You'll draw a vertical scale. These will be your frequencies or relative frequencies. Basically, how often do they occur? Okay? Or percentages, I suppose, with relative frequency. Now, what you'll do is draw a rectangle, basically, for the heights of how frequently it occurs within that particular interval. If there's no scores in that particular interval, you would put a rectangle and you just leave a blank space. So it'd show basically a gap within the data. Okay. So to give you some examples of some histograms and how you can construct it. Here's some data. I'll be honest, I just made this data up because I am a Costco junkie. I don't know about you guys if you like going to Costco or Sam's Club, but every time I walk into that store, I can barely walk out of there without spending $100. Sometimes it's $2, sometimes it's $3, and then I get in trouble.
Don't do Costco.
Okay. What's that?
Don't do Costco.
You don't do Costco? You're better than I see stuff and I love the deals. And man, when they have the samples out, ooh, that gets me in trouble even more. Some of you are laughing and smiling because you know what I'm talking about. They put out that chunky cinnamon bread, they give you a taste of that, you're like, ooh, that's good, I'll buy a loaf of that. So, anyway, Costco wants to look at how much a person typically spends on a trip to one of their stores. Sorry, didn't mean to bump you. Below is the data collected from 1,000 customers that visited various stores across the country on a little typo given day. First typo I've seen, and you guys have probably seen 20 of them. So, what's nice is they've set up the intervals here, $0 to $39, 39 or 40 to 79. So they've set up the intervals at about $40 each interval. And sometimes they'll do this with histograms because we know that, we could keep on going chunks of $40 because there are probably these 25 people spent even like $600, $700, $1,000 at Costco. You're like, oh, holy cow. You can buy furniture at Costco, you can buy computers at Costco, you can buy cars through Costco. That's how crazy it is. So sometimes what they'll do is if it keeps on going and there's not many data points in that interval, they might go something like this, 280 plus, okay? So it says make a histogram of the data above. So again, we want to construct our axis. Here, the x-axis, we're going to label it money spent. Okay. Our frequency, if we look at our frequency, it goes all the way up to, the biggest one will be 250. We had 250 customers spend somewhere between $80 and $119, roughly. So, since I'm going to 250, I'm going to count by 50s. 50, 100, 150, 250. And again, this is number of customers. So now, what's nice about my histogram, it actually starts at 0, and my bin widths are going to be every $40. So 40, 80, 120, 160, 200, 240, 280, and notice how I'm actually going to go to 320 because it's 280 plus. So it'll be 280 to even more, but I'll just go 280 to 320 to include those. Come on.
Why did you choose to have the y-axis be the number of customers?
You can flip it around, I suppose, if you want. I just like to do it because then when I draw a curve above them, it helps me see the skewness of the distribution a lot
I didn't know
easier.
if there was like a certain one like you did with a certain reason.
Well, most of the time histograms, the x-axis is going to represent the variable that we're looking at because really we're concentrating at, or we're looking at, you know, the amounts of money people spend at Costco, okay, on a given day. So that could be our title, money spent on a given day by a customer at Costco. So, from basically 0 to $39.99, I didn't put the 99 cents here, it was 95 people. So I'm going to go up to just under 100. Mine looks like it's at 100. Sometimes what they'll do with histograms, and I love it when they do this, I like to actually write the number above the bin. They like to call them bins with histograms and bars for bar graphs. So, the next one was 165. Notice how they're connected here. 250. 230. And then 140. 60. 45. And 25. See, my 4s, they don't like my 4s sometimes. Give you a little time to finish the graph before I do part B. Sorry, I'm standing in some of your guys' way. Started my life.
Yeah.
Right here. No problem.
Hey Bart,
Yes.
for money spent, how they have 0 to 39, you said it was nice how they already have that set up for us. Are we gonna have to set that up? Figure that out?
Sometimes you might. You'll have to look at the data and say, all right, what's my low score? What's my high score? So, like for instance, if they actually gave me this list of, 1,000, different dollars spent by 1,000 different customers. I look at what's the low and what's the high. And then I try to set my interval so that I get somewhere between probably like 10 and 12 bars. Or 10 and 12 bins. Or 7 and 12 bins. I'm not even talking correctly right now. That's what I get for working at a swim meet on Friday. I talked a ton at the meet. I had to announce 11 divers. Woo! That was a lot. So, let's look at the distribution here. And what I love about histograms, it's even easier to see what the shape of the distribution is. Because what you can do is just start to draw, I hit blue and it didn't change the color. If you were to describe the skewness of this, what would you say? Yeah. And the best way to do skewness, make a fist with your hand, okay? Have your thumb pointing out and put your hand on it. Your fist is where all the chunk of the data is, and your thumb is where the tail is pointing. So in this case, which direction is it pointing? To the right. So if it was going the other way, you'd have a smaller amount right in here.
Wait, can you say that again?
Okay? Make a fist with your hand, except keep your thumb out. Put it on your distribution or your graph the way like how it's pictured. So it would look like this. I won't put it this way because, I don't have a ton of data here. Which way does my thumb point? Which direction? To the right. So it's skewed to the right. It's a nice way of doing it. I'm guessing those that are watching the video can't see that, so I apologize for that. So, here we go. I'm going to move that up a little bit. So, our distribution of dollars spent at Costco, because I always want to put it in a context, is skewed to the right with a center around. Now this is where it gets even a little more interesting on estimating the center. So when I look at this, I have to think I had 1,000 customers, right? So customer maybe number 500 roughly would be the center. So let's see, 95 and 165 would make what, 260? And another 250 would make 510. So customer 500 spent somewhere between 80 and $120, but I don't know the exact dollar amount, but I know it might be on the higher end. So what do you want to put for a dollar amount? Around, someone throw it up for me.
180.
180, remember we want to be between 80 and 120,
98.
okay? And we want to be closer, I think you want to be closer to 120, wouldn't you? But I suppose I couldn't argue against 98 and 99, so. Alright, $100. Okay. To me, if your answer was between $80 and $120, I'd be okay with that. Okay. I myself would have put it at 110, 115, but I don't know for sure. I really don't, because I don't know the individual data points here. That's the downside of histograms. It's because you have a large number of data. You don't know how many of these dollar amounts are $80 and how many are 100 and how many are 115. Okay. So, our spread of dollars spent goes from about $0 to over $280. Now notice how I put about $0. I don't know if there was any customer that didn't spend anything. They're just going for the free samples. Right? There are people that do that. There's usually this old guy walking around Costco during sample day and he goes up there and grabs like 4 samples. You're just like, what are you doing? Okay. But I don't know for sure. Retired getting. What's that? Oh, it's Saturday is big sample day. Mondays can be sometimes. I mean, when it's a big sample day, they'll have like 10 to 15 samples going on. But I went to Costco on Monday, and they had probably about 5 or 6 people handing out samples, and they were handing out good ones. They were handing out the cinnamon bread. They're handing out like the cheese and turkey, and the chips with guac, and you know what? Sometimes they have really good samples, and sometimes you're like, no, I'm going to pass on that one. They had a sports bar that tasted terrible. It's like, you know, like, oh, this is like chalky. Ugh.
Yeah, trips to Costco.
Oh, I would love to do field trips to Costco. So, all right. Any questions with this one? All right, next page. Okay, so
Your grocery shopping list.
what's my shopping list at Costco?
Yeah, you do some sort of statistics about one.
You want to know what I buy at Costco right now?
Yeah.
Really? This is getting recorded on the video. That makes it really long. Poor people that have to watch the video.
That's alright.
I always go into the fruits and vegetables, usually get some salad, get some fruit. I vary the fruit. Sometimes it's grapes, sometimes it's strawberries. I usually will buy a watermelon all the time in the summer. So that's always good chopped up. Veggies, I always get red peppers and carrots. Okay, occasionally we'll get some asparagus.
Just talk about food.
Yeah, talking about food right before lunch is painful. Alright, so now, as I promised you yesterday, we would get into more formal definitions of shape, center, spread, and outliers. Right now we've been just kind of using some general rules. But we're going to get more specific so that when we start to describe center, we'll actually use specific values. Okay. Or when we describe spread, we'll use specific values instead of just saying going from the low to high. Because that's really doesn't help you a ton. Because lots of times you can just read that right from the graph. So, just to review shape, we've already talked about these. Symmetric, skewed to the right, skewed to the left. So I'll just draw a quick picture. Symmetric, left and right side are balanced. Skewed to the right, tail of the distribution goes to the right. Skewed to the left, tail of the distribution goes to the left. This has lots of low values. This has lots of high values. Okay? Remember in Algebra 2 when you learned about mean, median, and mode? And they always said mode is a measurement of center. It's really not a measurement of center. It's a measurement of shape. That drives me crazy as a statistician. Okay? When we talk about something and we look at the mode, we're really looking at its shape, meaning how many peaks does it have. Okay? When something is unimodal, that means the data has one peak. In Chapter 2, we'll talk about a normal curve, which has a single peak, unimodal. Okay? But all these that I've drawn above are all unimodal, meaning they only have one peak. But data can be what's called bimodal, where the data centers in like 2 areas and you have 2 peaks. So it might look something like this. Have lots of low scores, lots of high scores, nothing much in the middle. Once in a while I get tests like that, where a lot of kids will get it, and then a lot of kids don't. That always drives me crazy as a teacher, going, why didn't I get it to everybody? Multimodal. Okay? Okay, that's where you got multiple humps. Do the hump notes. Okay. Now, that shape, center, mean and median. Yay, you know these terms very well. Mean is the average. This is the formula. This symbol stands for sum. So basically, to get the mean, you sum up all your values and divide by the number of terms. N is the number of terms that you have. X bar is a symbol for sample mean. Because you're going to type in all your data from your sample. We'll use our calculator to calculate out means. Okay. I rarely calculate them out by hand. Median is the midpoint of the distribution. 50% of the data is above and 50% of the data is below. So if this is our distribution, the median is located where 50% of the scores are below it and 50% of the scores are above it. Your calculator will calculate out your mean for you also, but I do like to show you how you calculate out the mean by hand. Because when you have a small set of data, sometimes it's easier just to go and boom, find it. What's that?
Median.
Median. Did I say mean? My apologies to the video. Median, again, is what we're talking about here, is that middle data point. Divides it into two equal pieces, and we'll show you how to find your median. So, how the steps go is this. Arrange all your observations in order. So if they're not in order, put them in order. If n is odd, the median is just simply the center observation of the order list. If it's even, the median is the average of the two center observations. So I've given you two data sets here where you have an odd number and an even number of data points. So like on this first one, if I want to find my median, I'm going to count how many data points I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I did? 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. No. Okay. So I have 13 data points here. Now when it's a small data point set, lots of you might go like this with your fingers on one end and the other and you just count until you get to the middle. I'm okay with that. Mathematically, how I do it is I take whatever n equals, add 1 to it, and divide by 2. And that tells me that it's the 7th term in the sequence. It's not 7, even though it's going to be in this case, but it's the 7th term. So I can start here, 1, 2, 3, 4, 5, 6, 7. So it's this specific value, because notice how I have 1, 2, 3, 4, 5, 6 data points to the left, and 1, 2, 3, 4, 5, 6 data points to the right. When I do the second set of data, how many data points do I have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. So n equals 16. If I use this formula piece and go 16 plus 1 divided by 2, you might be going, well, it's 8.5. How can it be the 8.5 data point? That's where it's talking about it's the mean of the two center observation. So what you do is you take the 8th and 9th point and average them. So in this case, I go 1, 2, 3, 4, 5, 6, 7, 8. So my median is right in between here. Notice how it divides the data into two equal pieces. 2, 4, 6, 8. 2, 4, 6, 8. 2 above and 2 below. Or sorry, 8 above and 8 data points below it. So my median is technically 4.5. So I have to average 4 and 5. Notice how it divides the data into 50% and 50%. I know some of you might be saying, well, this includes this data point, so it's 50% and 50%. All right, can we go to the next page? Do that one kind of quick. Spread. We've already talked about the spread. Helps describe the variability. This is a word that we like to use in statistics, variability. Not everybody scores the exact same value. We've been doing spread by stating the lowest and highest values. That's okay. But there's more than one way to describe the spread. One way we can do it is by talking about the range. The range is simply taking the max score or max value and minusing the minimum value or score. So we might say the range of the data is 30 points. A more formal definition of measuring variability is what we call standard deviation. It measures the average distance observations are away from their mean. So it's the average distance you're away from the average. Okay. Here's a complicated formula for it. I'm going to show you how you do it by hand one time so that you get an idea of how it works, but we will use our calculator many times to calculate this out. So to give you an example here, give me 5 numbers, shout them out between 1 and 10.
7.
4, 7.
Oh, hang on here, that's a good marker.
12.
I heard 7 and I heard 3. Well, not between 1 and 10.
4.
4?
8.
8? 5. I know. I was avoiding your 2.1. Sorry, Jamie. I was doing that just because otherwise it's going to take me more in my head to average these up. So, first thing, in order to calculate out this formula, if we look at this formula, it looks kind of complicated. Oh my goodness, look at all these symbols. A square root. 1 divided by n minus 1. We have this sum, and it says xi minus the mean squared. Wow. What does that all exactly mean? Well, the first thing here is I'm going to calculate out this mean value. So, what do I have to do to these data points to get the mean? I got to add them all up. Yep, let's take the sum. What do you get when you add these all up? 27. Okay, so that's the sum. What do I got to do to get the mean? Divide by what? 5. That's our n, number of data points. So what do I get? Take your calculators if you need to. 27 divided by 5? 5.4. Excellent. So now, when we think about standard deviation, what we're doing is this. We're make a number line, and on my number line, I'm going to put the mean here at 5.4. I'm just going to make this kind of dotted line going straight up. What I want to do is look at the average distance each of these points are away from the mean. So, what I can do here is say, all right, we'll start with 7, and I want to use a different color. So, over here, 7. I'm going to just write 7 right here. I'm going to look at this particular distance. How far is 7 away from the mean? 1.6, because you're just going 7 minus 5.4. You get 1.6. So what's happening in the formula here is we're taking each data point and subtracting the mean from it and getting that distance, because we want to see how far the average distance it is away from the mean. We do it again and again and again. Now you can see why we like to use our calculators. Just think if you have 50 data points that we have to do this. So let's see here, 3. So here's 3. How far is that away? What's 3 minus 5.4? Okay, and I'm gonna technically put it as the formula negative 2.4. Need to do it for 4. So 4 minus 5.4. Negative 1.4. Let's do it for 8. I'm kind of doing a lot of math here, but 8 minus 5.4. And then the last one is 5, which is a lot closer. 5 minus 5.4, negative 0.4. Now here's the thing. You might be saying, okay, we just want to average all these distances. What happens if you add 1.6, negative 2.4, negative 1.4, 2.6, and negative 0.4?
Oh, well, I was just wondering why it wouldn't just be 2.4 instead of negative, because it's just distance. Right?
And distance is positive. I wholeheartedly agree with you, right? That, and we're going to deal with that negative piece in just a second. The reason why we have it be negative right here is so there's a consistency with the formula so that you're always going your score minus the mean. Instead of saying, well, do I flip them? How do I deal with the negative and the positive? So we need to have a consistency among every single data points or every single data point and how we treat it. Okay? So hence why we have the negative and the positive. And here's where the negative causes the problem. When I go back to this question, what happens when I sum these up? What does it sum up to? What's 1.6 and 2.6? 4.2. What's negative 2.4, negative 1.4, and negative 0.4? 4.2. If you're thinking about comparing data points to how far it is away from the average, whatever points you have and wherever they're located, the left side and the right side will counteract each other because you're comparing it to the average. You're comparing it to basically the center point. So if you add these up, what's 4.2 and negative 4.2? 0. So if you don't deal with these negatives, they're always going to sum up to 0. So the standard deviation formula won't work. So as mathematicians, how we've decided to get rid of the negatives is by squaring it. Because what happens to numbers or negative numbers when you square it? They become positive. So what we now do is we take all these values. This is where it's going to be a little more fun for Mr. Barth because we have decimals. And we're going to square all these values. So 1.6 squared, I think is 1.96. We've got a calculator real close. I think I'm right on that one. 1.6 is, oh, it is 2.56. Oh, Mr. Barth, come on. All right. 2.4, negative 2.4 is 5.76. 1.4 is 1.96. 0.6, ooh. Yeah, I think, what is 26 squared? 6.76, I think. And 0.16. These are the values that we will actually sum up. So, 5.76, 2.56, 6.76, 1.96, and 0.16. We're going to sum all these values up. Can someone kindly in your calculator, Jamie, since you have your calculator right there, do you mind summing those up for me? We can get a check. Oh, it's going to end in a 0. Get my math right. See if we agree. Yes. Alright, so they sum up to 17.2. So what we've done here is we've actually done this part of it. We've done the summation of all those values. So now what it says is multiply it by 1 over n minus 1, or what it says is, take your data points, or take this value, and divide it by one less data point. So instead of dividing it by 5, we're going to divide it by 5 minus 4, or sorry, 5 minus 1, which is 4. So, take 5 minus 1, 4. Let's go 17.2 divided by 4. What do we get? 4.3. That's our average standard deviation. Now, is anyone wondering why we divide by 4 instead of 5? Because average, usually you do it under the total. No one's wondering that?
Sure, let's roll.
Oh, thank you, Miss Allison. Okay. Well, if you only have one data point, okay, if you have 5, say if my data point is 5, what's the mean? Okay, the mean's going to be 5. Okay, since we're talking about measurement of spread, okay, we're talking about distance away from the mean. Can you have a spread when you have one data point? There's no way to even start to calculate it out. You can't even figure it out. You need a minimum of 2 points in order for you to be able to even calculate out a spread. Hence why we subtracted from 1, because you need at least 2 to get your first measurement of spread. Does that make sense? Takes 2 data points to get your first, so 2 minus 1, hence why they're going n minus 1 here. And that's going to be important in a lot of our formulas that you'll use. You'll see that we'll divide by n minus 1 or n minus 2 when we start dealing with linear regression. That's a few chapters from now. Now, if you have your graphing calculators, take those out for a second, and then mine's going to pop up here. If you don't, follow along with the neighbor real quick. Thank you. Can you ladies screen down? Thanks. All right. So, this is a lot of work, isn't it? To calculate out standard deviation by hand. I don't know about you, I don't really want to do it by hand that way. I want to find a much faster and efficient way of doing it. But understanding that standard deviation is the average distance my data is away from the mean is very important. So, if you go stat to your stat menu right here, so on your calculator, look for the button that says STAT. It's still highlighted red here. This is why the 84s are so important, because that's what I use up here. It'll be easier to follow. Go to your edit menu. Okay, I have tons of data in there. You might have tons of data, you might not. To get rid of the data, this is so important. Use your arrow, highlight the list, and hit clear. Do not hit delete. Hit clear. If you hit delete, you remove L3, and then you're like, oh, where'd my L3 go? Or where'd my L1 go? And then we got to reset your editor, which isn't the end of the world, but I can guarantee you at least 10 of you sometime this term will come up to me and ask me, where'd my list 1 go? I can't get my list 1 back. Stat. Edit, number 1. You got list 1, you're perfect. Now, this is what I want to do. Just to verify that the standard deviations thing that we just did is done correctly, let's type in those values.
Wait, so do we have to do it longhand when you ask us to do it?
No, I never want you to do it longhand.
Okay, good.
This is the only time you'll see it done longhand. I do a very small data set longhand just to show you how cumbersome that formula is. But it also hopefully gives you a picture and it helps you realize what standard deviation represents. It's actually calculating out average of those distances. So now, once I have my data in my list, okay, you can exit out, second mode. go back to statistics, stat, and this is a menu you're gonna love, or get to know, love, make your best friend. Nick, you're gonna have lots of friends in here. Jake's not your only friend. I don't even know if Jake's your friend. No, I'm just kidding. No, not really. So, pick edit. Oh, sorry, my fault. Go back to stat. I didn't mean to hit edit. I was backtracking. But what we want to do is calculate out the standard deviation. So go over to calculate. This is a menu that you were doing back in your Algebra 2 days. We're going to select one variable statistics. One variable stats. Now, if your data is in a different list, you have to type the list after it. If your data is in list 1, that's the default list. So when you hit enter, it's going to do everything on list 1. What do you notice the first value it gives you? X bar. What's X bar? 5.4. Look at this. Did we do the sum of x's earlier? They summed them up for us, 27. Sum of the x's being squared, something we don't use yet. S of x. What's the symbol for standard deviation? In your packet right there. S. Standard deviation of my x's, which is what we're doing. They get as, why did we have, oh, I know why. I screwed up. I was like, wow, that was a nice number, 2.073. What have I forgotten to do with my standard deviation? This was the sum of them squares. What do I still need to do? I knew I forgot to do something. I have to undo the squares by, okay, so let's take 4.3 and take the square root of 4.3. I'm looking at that going, wait a second, that's not mine. So, I can even do it on my calculator. So, square root of 4.3. Oh, that's not what I asked it to do. The square root. I stand so close I can't even see the square root symbol. Alright, 2.07364 da 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 la 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 la. So if I go to stat, calculate, and I do that one variable statistics, did it give me the exact same standard deviation? Okay? So, by taking the square root, we got it. Again, this is the average. So whatever those values represent, our data points on average were 2.07 whatever away from the mean. Okay? Now, the variance is another measurement not used very often, but it does come up time to time, is simply the square of the standard deviation. So it's this formula that we calculated out when we got 4.3 on our example up on the board. Okay? We took the square root of it here to get our 2.073. So, just for some quick practice, I want you to type in this data list in list 1. And I want you to find the spread, the range, standard deviation, and variance of this data set. Ready, set, go. Yeah, you guys gotta, on your way to lunch, stop at the library and check out calculators if you don't have one. Because you need one definitely for the test.
Mr. Barnes,
What is what?
when I hit I went over to calc and then brought stats.
Oh, it does that? Okay. It works,
But
but
when I
you just gotta go.
calculated that, it was like,
Yeah,
it was a
what
5.4 as the,
what I would do, can I just change something
yeah,
on here?
of course.
What happens is these calculators have what's called the stat wizard. And I'm gonna turn that off, since I'm here, I'm gonna turn your diagnostics on, as well as do that later. So now it will be run like how I do it. So it looks like you already typed that.
Yeah, they can know what your
No, it gets so cold in here. I feel my nose running.
Yeah, no, I have allergies.
Oh, well, you have allergies, you're allergic to everything in this school.
Annoying.
Because this school has everything in it. I feel.
I was allergic to majority of the nutrients in Minnesota, ragweed, cats, grass.
Oh, alright, hopefully time's sake you have these all. Spread. What? This data goes from what to what? 18 to, thank you, range. 56, again you go 74 minus 18. Standard deviation. 39? Okay. And variance. What was the standard deviation? 18.89, that sounds right. Variance, what would I have to do with this value? Square it. So take the 18.89 and square it, what do you get? It's like 300 and something. I'm gonna say 356 point. Beautiful. Where are you getting that? You're just taking 18.89 and you're squaring it.
Alright.
How long do we go
Is that
until?
83?
83, yes. So,
29.
okay. Alright, next ones. Quartiles. Quartiles mark out the middle half, okay, of the data set, meaning this. If my data goes from a min to a max, your median divides it into 50% and 50%. Your quartiles basically takes the median of the lower half, which is Q1, and the median of the upper half, which is Q3. So it divides your data into 4 quarters, hence why they call it quartiles. Quartiles, quarters. Then you'll average them. Or if you have like, so, just like you do median, you would like average the data points if necessary. Now, lots of times in a data set, we'll look at the interquartile range, which is simply Q3 minus Q1, otherwise known as the middle 50% of values. It's the middle 50%. So this distance from here to here is my IQR. Now the interquartile range is another measurement of spread that we can use, and it helps us a ton when calculating out outliers. You ready to go to the last page?
Yes.
Anyone still need this page? Okay. Outliers. As we've been talking about potential outliers, it's just an observation that falls way outside the overall pattern. Okay. So how do we classify an outlier? Here is our formula. Okay. So what you have to do and what it involves, and I'll rewrite it here, is how I like to write it is this. Outliers are values that are greater than the third quartile plus 1.5 times your interquartile range. Or they could be values that are less than Q1 minus 1.5 times the IQR. So what could happen is I could have a data set that looks like this. I know I'm kind of drawing a box plot, which some of you have seen in Algebra 2, and we'll revisit this tomorrow. Or sorry, on Tuesday. So this is my min. This might be Q1. Here's my median. Here's Q3. Here's my max. So what happens is for an outlier, I go from Q3 and I add 1.5 times the IQR to it. So that distance might go to here. Anything here would be considered an outlier. Likewise, going in this direction, I'm taking Q1 and subtracting that 1.5 times the IQR. I'm going out that distance, and anything that's less than that is considered an outlier. Kind of hoping that visual helps you see and understand how this formula works. You're taking Q3, you add 1.5 times the IQR to it. Anything above it, outlier. Subtract that distance from Q1, anything below that is an outlier. Okay. Now, the last couple concepts here that we'll talk about is this first thing called a resistant measure. Okay? As it says up there, a resistant measure is a measurement that is relatively unaffected by extreme outliers. Meaning an outlier is not going to really change its value that much. Okay? Median and IQR are considered resistant measures. They don't change very much. Okay? However, mean and standard deviation are non-resistant. So when we start to look at data, if something is symmetric, okay, I will use the mean and standard deviation to describe the center and spread. However, if something is skewed or has a lot of outliers, if it has one, depending on it, I might still use mean and standard deviation, but lots of times outliers will change things drastically to the mean and standard deviation, but it doesn't affect the median and interquartile range that much. Okay? So just note which ones that we'll tend to use depending on the shapes of those distributions. So, here's our data set. It says, given the following data set, find the first quartile, find the third quartile scores, and the interquartile range. State the scores that would be classified as outliers. Okay? Now, I can show you how to do this on your calculator, and I'll do that with box plots. But I'm actually going to do this one by hand real quick. Okay? In order to find the first and third quartile, what do I have to find first? Median. So how many data points do I have here? 14, 15, 16, 17. So if n equals 17, if I add 1 to it, divide by 2, it's the 9th data point. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 41 is my median. So now to find Q1, it's the median of these 8 data points. Q3 is the median of these 8 data points. So 8 plus 1 is 9, divided by 2 is 4.5. So I'm looking for the average between the 4th and 5th data point. 1, 2, 3, 4. There's Q1. Q1 would be equal to what value? 26. Now that I've done that, it's between 4 and 5 here. 1, 2, 3, 4. Q3 would be,
74%.
so I got to add those yet, 74.5. So I have Q1 and Q3. Are you guys okay how I did those? Just median, median, median. Do the median of all the data. Median of the lower half, median of the upper half. So now, interquartile range, IQR. Simply Q3 minus Q1. So 74.5 minus 26. Is that 48.5? Am I going too fast? No? Okay, good. Now it asks you to state scores that would be classified as outliers. So let me switch colors here. Outliers. Again, scores that are greater than Q3 plus 1.5 times IQR and less than Q1 minus 1.5 times IQR. So let's see here. Q3 was 74.5. I need to subtract 1.5 times IQR. So 1.5 times 48.5. Wow. I use my handy dandy calculator on my head. I think that's 72.75. Half of 48 is 24. Half of 50 cents is 25. So 24 plus 48 is 72. 25 cents plus 50 cents is 75 cents. That's how I did it in my head real quick. So I need to add that to 74.5. So I get, wow, 146.75. So an outlier would be a number greater than 146.75. Or it could be less than 26 minus that value. Whoops. Which would be what? Negative 46.75? Oh, or that's not right.
Wouldn't it be 47.25?
Yes, I realize I did that wrong.
On the top. No, on the top one.
Oh, on this one?
Yeah, would it be 47.25?
Yeah. Dang it. Thank you for the correction. I didn't add correctly. Mr. Bartz. The handy dandy head calculator failed. Thank you for correcting that. 'Cause I can't add. Alright, let's do the subtraction. I do the subtraction here right. 26 minus 72.75.
Negative 47.
Negative 46.75.
0.5. Oh.
Or it should be negative 46.75, right?
Yeah, I just.
Do we have any data points in our list right now that meet that criteria? No. Okay. Alright, one of the things that I just want to show you just real quick, and then I'll let you work on CFUs and check off homework, goes back to this resistant measure piece. Okay? We're just going to do this by hand real quick. Here's my data set. 1, 2, 3, 4, 5. What's my mean? Really? 3. What's my median? 3. Okay. Now I'm going to have some fun. I'm going to add the data point 60 to it. Okay. What happens to my mean? 1, 2, 3, 4, 5 adds up to 15 plus 60 makes 75. What's 75 divided by 6? Someone do that on the calculator right away. 75 divided by 6. 12.5. What's my median? It's right in between here, 3.5. Notice how the mean drastically changed when I threw in this one outlier point. But did the median change much? No. Same thing happens with the standard deviation. It's going to change drastically because your average spread, because 60 minus 3 is 57, now you're going to square it and add it into that piece. It's going to cause standard deviation to get much bigger. But your interquartile range, that's not going to change very much. Your middle Q3 and Q1 are still going to stay low. Okay? So that's what it means, and that's the key piece with resistant measure. Okay. All right, we have 1.5 and 1.6 notes completed.